there. Okay, filter design. Let's take the look at what it is all about. So a brief summary of filter design again. More about that one. There are plenty of books on filter design, online books. But anyways, I'll show you some of the principles, general principles on the filter design. This is basically something you have heard before, but just as an introduction to the topic. So basically there are these practically 5 different kind of filters classified by the spectral response, and then there are digital filters are categorized by FIR or IIR systems. Topics from the was it third session, and when we are looking at a low pass filter, then there are some of these parameters there, like passband. Passband is generally the defined with the -3 dB point, unless you have a ripple on passband, then this attenuation level could be something else. But anyways, that's a passband. Then there's a stop band. Stop band, which is basically defined by the point where you have enough of attenuation. So practically, if we had in this picture, if our the requirement for stop band would be 15 dB, then our stop band would start a little bit earlier. So basically the same thing as the passband. This where the passband ends, that corner frequency, it's defined by some dB level. For flat passband passband filters, actually this -3 dB, but could be something else. But even more on the on this attenuation, there you basically have a required attenuation level, which also defines the stop band. And in between, there's a transition band. So transition band is just a band between passband and stop band. Same thing for the high pass filter. It's just, the mirror image, exactly mirror image actually. So passband is, of course, there on the right, and the stop band on the left. In between, there's a transition band. For bandpass filters, nothing else changes except that we actually have 2 different attenuation levels. We have the lower frequency, lower attenuation level, lower stop band, and we have higher stop band. And we have also 2 transition bands, which can be totally different. As in here you can see the transition band 1 is shorter than transition band 2, and then the stop band attenuation on the higher stop band is bigger than in lower stop band. Then we have bandstop filter. Okay, that's practically the opposite of the bandpass, which have the 2 pass bands, lower and higher. If you are talking about filters, then usually you are matching it to unity gain on both upper and higher. Otherwise, you are talking about, say, mixers, equalizers. But anyways, we have passband, one transit band here, another transit band here. These don't need to be exactly the same since the transit bandwidth or could be a little bit different requirements depending on the requirements. Okay, then we also have some certain filters in analog filters, for example, Chebyshev's filter or elliptic filter. They let's see, elliptic filters. They have ripple on passband, so that one actually defines the passband on the for this kind of filter with the passband ripple. Otherwise, it's the same. Okay, let's start from the FIR filter design. There are two good reasons why to use FIR filters. And if basically, if you don't need linear phase response, then usually you don't need FIR because FIR filter actually requires more calculations. But anyways, the easy part is it's always stable. You have only the impulse response there as the parameters of x, and basically the linear phase response comes if the h of n is symmetric, either positive or negative symmetry. Now, three methods, and I will go just for fun the impulse response truncation. That's basically simplest way of measuring a system and defining the transfer function. But anyways, there are more sophisticated methods to do this system characterization based on the same measurements. But it's a nice way to start. Impulse response truncation. Then windowing method, simple design flow, but not optimal. That's easy actually. There are some optimized design methods, which is the way to go, but that usually comes with a say toolboxes like in MATLAB. They have these optimized methods, least square methods, for example. Okay, so let's take a look at first one. Impulse response truncation. Simple method. We measure the step response of the system. We sample the step response and use differentiator to get impulse response and compare to analog frequency response. Okay, yep, sure, that way. There's an example. So RC, low pass filter, I have the connections here, a simple connection, and that's the amplitude response. And when you're running a square wave there with fast enough rise time and then also the low enough the frequency, then you would get a picture which looks like more or less like that. So it's not perfect square wave as you never get, but it's a close approximation. And yeah, that blue curve here, that's the measured signal, quite familiar, okay, but that's also digital sampling oscilloscope. So that's the measured waveform step function and step response. DSO, digital sampling oscilloscope. So actually I just took the data and truncated. So this data was considered as S of n. Then I took the first order, the differential, meaning that just, well, let's see text somewhere in here. Oops. Text here. So the h of n, oops, equals that S of n minus S of n minus 1, as we had this one earlier. Clear that one. Stop annotations. Okay, so from that one, that's a then basically I just compared the analog system, since I knew the RNC, and the digital system, which was calculated from the impulse response. The Fourier transformation of the impulse response gives me the amplitude response, and they are quite okay until you hit the noise floor. As you can see, there's quite a lot of noise. It's 8-bit converter plus my setup is not ideal. It's basically, I have long wires there, and these leads the are not really great for any signal. So you get long leads without any protection, and then basically it means that it picks up all the fluorescent light pulp peaks and nearby power supplies and everything. So it's a noisy as, very noisy. Let's put it this way. Okay, and yeah, so this is as much as we can get out of the juice, out of that method. Depends, of course, how well you can make the ideal setup for your measurements. But anyways, it works. I got the h of n, and it gives me, say, quite nice, uh, similar amplitude response as my analog system, up to, say, almost 20 kilohertz. Yeah, then it hits the noise floor. Okay. This comparison is between this the analog and ideal digital. This method actually fails always at higher frequencies because you are truncating your impulse response, which means that then you are missing some data, and basically this is actually aliasing, which happens at the end of the spectrum. So on that, I would say that truncation of impulse response is not good design method, but okay, it's a design method. You couldn't get what step 4 was. Yeah, that was about compare. Yeah, that's extra. I compare this one on this exercise, compared the analog and that digitized system, the amplitude frequency responses. Okay, so next step, windowing method. So this is actually a method you can use. It works really well, and you get, say, predictable answers to your filter design. So where it starts, it's an ideal low-pass filter with desired cutoff frequency on in continuous time. system, meaning continuous time and also frequencies from minus infinity to infinity. On continuous time, we make the inverse Laplace transform to continuous time impulse response. Okay, so directly from the low pass filter, the amplitude response directly using inverse Laplace transform to make the continuous time impulse response. And then we are sampling that continuous impulse response. And then we get the this discrete time system, discrete time impulse response, which is now, okay, also infinite in length. But then you basically truncate it by windowing. The same way we have been watching this data through a window, we are just selecting our region of interest on that impulse response graph and use that one. Okay, so, but anyways, step 4, use an appropriate window. I'll go through this more detail later. To smooth the edges. The problem of watching the data through the window was that you get in spectral space, you get these winglets for the spectral spectral peaks. But we can actually smooth the edges of the impulse response. And then actually the last point would be to adjust the width of the truncation for getting a this stop band attenuation. No, sorry, transition bandwidth. Good enough. So the stop band attenuation is actually characterized by. Sorry, I had to get a drink. Oh, well, just a sip of water, not a drink. Something lost in translation. Okay, so this is the step 1. Ideal continuous time low pass filter with cutoff frequency of, well, that cutoff frequency is defined by the minus 3 dB point, which is, well, minus 3 dB would be somewhere here, doesn't matter, it's a box. So this is an ideal. And actually, let me annotate to remind you something. So draw a line. This normalized frequency goes from minus infinity to infinity.
Sorry, isn't it
So
bandpass?
Yes. Low pass.
But
See, the zero frequency. Zero is here. This is the positive side is on the right hand side and negative side is on left hand side. Yeah. So yeah, sorry, I didn't. good question. So yeah, so for the mathematics, I would like to have it like that. So it's for symmetrical in frequency space, meaning that the Laplace transform will be giving the real numbers. Otherwise, you'll get complex. Okay. Good note, though. All right. So yeah. So 0 is at the middle. And on both sides, we have this minus 3 dB point is now at 0.5 normalized frequency on this example. Just a moment, I will clear that, go forward. And when we take the inverse Laplace transform, it's probably something you have done on engineering mathematics already. The rectangular window will end up being a some constant times sine of pi x divided by pi x, which is defined a function sinc x is defined by that. By the way, there are two definitions. One is the mathematicians and one for engineers. This is the engineering definition where you have the normalized frequency. So mathematicians define sinc as sine x divided by x. So don't be confused on that one. But okay, so if we have a sampling rate known, then basically this constant and everything will end up being 2 times minus 3 dB points divided by sampling rate. That's the constant in beginning, and then sinc of 2 times the cutoff frequency times the indexes divided by fs. Okay, great. So there's a formula that we can use. And here we have the, well, the blue one is the continuous sinc. The green one is the window, in this case, rectangular window. And then we have the h of n. Why do I have h of n divided by fs? This is artifact. Sorry about that. I need to fix that at some point. But anyways, so we have the sampled impulse response, which is now defining an FIR filter. FIR filter coefficients are defined by these samples symmetrically on both sides of origin. Okay, good. Something to use. I should then actually, I will first show you this one. This is what you get when you are taking this h of n and calculating the this is amplitude or response in linear scale. Okay, doesn't look that box anymore, but there are few nice things about it. One is that it is a low pass filter, what we started from. So we started from a box. It has some ripple though, and the stop band attenuation is not infinite. But we started from ideal, so basically this resembles quite a lot already what we are looking for, and especially that minus 3 dB point, which is practically you fix the minus 3 dB point just by using the sinc function correctly. Okay, so sinc function, and where these do these artifacts actually come from? Well, thinking of this impulse response here, you are actually multiplying that sampled sinc. Okay, yeah, sampled continuous time. Okay, that makes sense. Now, sampled continuous time, the impulse response is now multiplied by the window. So we actually have this window shape. In frequency space, we have Yeah, okay. We have the multiplication in time space, which is same as convolution in frequency space. Okay, so what is the end result of that one is that this is showing the convolution between the box, which defines the minus 3 dB point here, and the uh, Z transform of the box. So sync gives the minus 3 dB point, and then the box gives that kind of variation here. Okay. Same in logarithmic scale. So typically the FIR filters look something like this. Okay. Um, now one point is fixed, so we can control the cutoff frequency. Great. What else? Now, in my point of view, this stop band is not good enough. Only 10 dB attenuation here and only goes to not even 20 dB attenuation, because that box there, think of now the Fourier series of box kind of or rectangular shape, the these functions. When you break it into uh, spectral components, you have a lot of power in high spectral components. In order to get this on time space, you need to have high frequency components, especially for this edge here, rising and falling edges of the window. Okay, if you want to reduce the amount of spectral components on this higher frequency, then basically you can smooth the window edges. And there are some smooth window shapes. These are quite kind of classic ones. By comes from the name who was inventing it. So a person called Bartlett found out a triangular shape, which is, yeah, it's what it sounds like. It's just a symmetrical triangle. And even that one gets already better stop band attenuation. So you can get up to 40 dB. If you use half cycle symmetrically biased cosine, well, I'll show you some pictures later, then you get up to 80 dB already. Then there's that Hamming window, 60 dB, and Blackman window, maybe my favorite. Half cycle cosine and full cycle, something harmonic. Okay, 80 to 90 dB. And those are the window shapes. Sorry, the does not quite show, but anyways, that's the window shape of box. I got it from here. So from here, left and right, they are just zeros. And this Bartlett, green one, triangular, already has better spectral properties than this box. And it's very simple to implement. Not that these other would be any more difficult to implement, since those have, say, functional forms. So Hamming, Blackman, and Blackman, as you can see, it's maybe the smoothest one. On the other hand, it also it reduces a lot of data points there, but Here you go, Bartlett, Hamming, Blackman, they go, the attenuation goes down and down and down. Hamming is nice, actually, since it's almost the flat on stop band. Okay, so, but anyways, as you can see, all of them have the minus 30 dB point exactly at the same point, as it should be. This is the window shape, whereas the sync function defines the cutoff frequency. So practically now we have a method to control the stop band attenuation based on the what is the requirement. Okay. Third parameter, when we think back, there was that passband, stop band, and then the transition band. So transition band, or basically where the stop band begins. If we want a short transition bandwidth, then we basically must do something for the system. Since, well, the window shape doesn't do anything. Well, it does do something. As you can see here, more you have the stop band attenuation, wider your transition bandwidth is. So in these, the box has the shortest transition bandwidth. It just sucks on this attenuation, stop band attenuation. But any of these, which wherever you have more and more attenuation on stop band, basically it comes with the cost of having the wider transition bandwidth. But actually, there comes the mathematics again, helps us. Multiplying of time is division of frequency. Yeah, makes sense. For example, if the transition bandwidth should be half of the original, we need to take 2 times wider window. So here I started, by the way, usually on this window method, you use odd number as the number of parameters, meaning even order number for the filter. So the first one here, 11 points wide, and then I multiply the time, meaning I take wider window width. So I take 21 points instead of 10 points, 11 points to the this calculations. Okay, the transition bandwidth is actually half the previous. Then I double it again. I get this one, double it again. There. If you need to have exactly something, that then you design a filter with the correct sync to get the cutoff frequency and the correct window shape to get the attenuation, and then you fix the window width by checking how much you need to go either down or up on the transition bandwidth. Okay. All right, so that was the low pass filter using windowing method. How about having the bandpass filter then? Actually, that's again something that we can learn from math, and well, this has been engineering for a while. So frequency shift, AM modulation. If you want to transfer the something on radio, the easiest way would be the amplitude modulation, although then it's the range dependent. So usually you use frequency modulation. But anyways, for this one, since we are not using any media, we are just multiplying this frequency response, not frequency response, the impulse response, modulate it with a modulation frequency, set modulation frequency. It does the same thing for this spectrum as it would do for the signal, of course. Signal, impulse response, same thing. In a sense, actually, the impulse response is just a special case of a signal. Okay, so frequency shift of that impulse response basically moves the spectrum of that low pass filter on the both sides of this modulation frequency. Okay, just a reminder that now if we had a 3 dB point or cutoff frequency at, say, in this example, 100 hertz, then the bandwidth of this bandpass filter would be 2 times that. And also the magnitude is scaled by half, but you know how to make the unity gain filters. Okay, that was how you make the bandpass filters. This is how you do high pass filters. It's practically just modulation by sampling rate divided by 2. Okay, sampling rate divided by 2 is the highest frequency. It's a Nyquist rate. And basically, if you do the modulation, then it just shifts this part. Okay, maybe I'll note it again. Draw freehand. So remember, you actually have this kind of curve. Oops, yeah, I'm still sucking the. I'm really bad on these graphs. Ah, okay, on both sides. It actually is both sides of the positive and negative signals there. So low pass filter came as a high pass filter, but remember that now the high pass filter cutoff frequency would be that Nyquist rate, the fs over 2 minus the original cutoff frequency. Since, well, cutoff frequency is relative to 0 frequency, while the bandwidth is relative to the, well, the lowest and highest frequency on that band. Okay, but anyways, low pass to high pass is to do. Band pass or band stop filter. Well, if you have the same order FIR filters, you just add the impulse responses together, you get a band stop filter with some sacrifice on the stop band attenuation, since you are adding the stop band attenuations together also. So with the phase, meaning that this will be a little bit surprised what comes out. So stop band attenuation, it can actually change up to 6 dB. So 60 dB less attenuation. Okay. Summary. Select the minus 30 dB point of low pass filter, and then you use the sync function. Then you select window shape for stop band attenuation, and then you adjust window width for transition bandwidth. And if needed, then you can transfer that low pass filter by modulation to band pass, high pass, or band stop. And okay, you can then start doing multi-band filters also by combining all of that kind of stuff together. Okay, and that was the windowing method. On the exercise, I will show you some tricks how to actually do a FIR filter design by windowing method, but there are also some more powerful tools on the even on Octave. If you are using MATLAB and have the signal processing toolbox there is a filter design and analysis tool. You can use that one. Just make sure you, when you answer the questions, you actually include necessary information that I can see that you have done it to the exercise, and not just guess the answer. Okay, but anyways, um, now you have one method to do FIR filters, design FIR filters, working methods. Then some words about IIR filter design. Okay, first of all, IIR filters are never linear phase, never ever. But most of the applications don't care. For example, audio processing don't care if it's a, say, voice or something like that. If it's communication, then you might have a need there. But on the other hand, if you are using post-processing, then you can always make linear phase response, non-linear phase response to zero, uh, zero phase response by a trick. I showed that trick already on, yeah, on the responses. So that was the zero phase shift. But IIR filters are most cost efficient, much better amplitude response with lower number of calculations than in FI, the same similar FIR filter. So applications, well, basically almost everything. So audio filters, equalizers, feedback reduction, high Q factor. IIR filter actually is, well, when you take a look at it, it's actually a control loop, feedback control loop. It has some more complex design methods. A pen and paper, well, I'm not going into the pen and paper version of it. Just mentioning, okay, this has been done in past, but I do not recommend basically any of those pen and paper methods on IIR filter design, since we have tools. Okay. So IIR filter design methods, there is so-called bilinear transformation, which starts from the analog filter model. It has this transfer function of h of s, and there you replace s with 2 divided by sampling time, or 2 times sample rate, times z minus 1 divided by z plus 1. Okay, simple. And yes, there are some pre-written functions to do it. So those digital filter design of the old-fashioned Butterworth, Chebyshev, elliptic, Bessel kind of filters. It starts from the analog transfer function and uses this bilinear transformation. What is the Now this is actually a simple method. It does not have aliasing effect as we had on that funny FIR, the impulse response truncation kind of thing, but it warps the frequency space, since actually on the frequency space on analog systems, the frequency axis is on S plane from -infinity to infinity on J axis. While in digital systems, our frequency actually is with the unit amplitude, it's on the this Z plane on the unit circle. The angle of the point in unit circle. So this actually takes the -infinity and bends it to a lower half of the circle and the takes the +infinity and transfers that into the positive half of the circle. So it's really warps the frequency space badly. It's not time warp, it's a frequency warp or space warp. Okay, parametric modeling is the second filter design methods, which starts with the differential equation of an analog system. So actually the starting point is the transfer function, but as differential equation. Remember that transfer function is actually Laplace transform, and Laplace transform is a part of it's basically relative to integral. That's the way to integrate. So differential equation, when you integrate it, or use the Laplace transform on differential equation, you actually get the transfer function. But anyways, it starts from the differential equation and then replace time derivative with discrete time derivative, first order derivative here. Okay, so first order derivative would be this one, and the second order would be, well, this squared divided by ts squared, and so on. Well, no, not that way. It would be just cascaded that one. So the frequency space remains linear, but aliasing distorts the performance, since we are doing this approximation of from the continuous time to sampled discrete time system. So that's where we make a error. But there, as I said, aliasing distorts the performance, but it works with high enough sampling rates. Okay, so that's a, say, adequate in some modeling. It's an approximation, so it works sometimes. Sometimes it doesn't. Direct design. Change the system coefficient recursively to minimize the root mean square difference between desired and real amplitude response. Okay, that's kind of, there are some routines that does it for you, and basically optimized methods, when you make a code that does it, then it's basically, we call it as optimized method. Okay, what comes to the example on direct design, bandstop notch filter. You start with a point on unit circle. You know that there you have the infinite, the attenuation, the amplitude response go to 0. We have practiced that one already. But at the same same frequency, you can put a pole So basically, when you think of the graphical representation of how to calculate the amplitude response, if you have a point here, which is at the same distance as the pole to 0, you have a point here where you calculate it. That green line in between is roughly square root of 2 times a. Not exactly, of course. This is again approximation. But anyways, square root of 2. So this was the on numerator distance. This is on denominator distance. On this point, those pole and that 0 are about the same distance. Maybe I should annotate again, just to remind you. So when we are calculating the age of okay, it's just e to e to j omega e to the power of x. J times omega. Okay, that's like that. With Lewis theorem. On upstairs we have z 0 minus z okay, z minus x. That's the point times z1. Oops. z1 minus x. Okay, something like that. Oops. Great. More text. And we have downstairs we have the p0 minus and so on times oops p1 minus da 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 divided by so okay, so this distance here would be a. That distance here would be square root of 2 times a. This distance and that distance would be equal, roughly. They're about the same. So actually what we got here is the same distance as we are from the is there between the pole and the unit circle. We have the minus 3 dB point. Great. That is just great. So practically we can define, for example, our minus 100, the 100 hertz point here, and then calculate the by the requirement for the bandwidth requirement. We calculate the minus 3 dB point, and that's the distance of that pole to the unit circle. Great. Yeah, that's also magnified. Okay, so that was a kind of direct method and only filter you can actually do by the direct method. But on the other hand, there are also functions to do it with a function if you find them. But anyways, then we have these classical filters. We have Butterworth, Chebyshev, and elliptic filters. So Butterworth, if you remember, that's the flat response on passband, while Chebyshev type 1 has equal ripple on passband and high attenuation on stopband. Okay, and then elliptic. Elliptic is the hard to tune, but not really in the in digital domain. In analog domain, this elliptic is quite hard to implement. Anyways, the elliptic has a equal ripple on passband, also equal attenuation on stopband. So it has also these zeros on the stopband to stabilize the stopband attenuation at certain level. Okay, but anyways, these are classical filters based on analog filters and transformed into digital space using bilinear transformation. Okay, and then this is how you make zero phase filter, meaning if you have an IIR filter, then you can filter the data first on one time direction and then reverse the time and apply the same filter again and then reverse the time back with what it was. And that's our output. And of course, non-causal. But if you have post-processing data, that's fine. It works like a charm sometimes. Okay, which is, sorry, I didn't watch the chat window here. When the notch value in imaging complex coordinator, then means that what is notch value? Okay. So yeah, I will show you the notch thing later on, but the notch angle here would be, for example, that 100 hertz. So, but anyways, you fix the notch basically by selecting the corresponding angular frequency. And that gives you the angle. And then you put a 0 on unit circle. It gives you the maximum attenuation where the amplitude response goes to 0. And then you put some gain on the same frequency by adding a pole on the same angle. And then you adjust this minus 3 dB point by moving the pole close enough to the unit circle. I will show you that in the.
I mean, sorry. I mean that notch angle get 90 degree.
Huh? Oh, sorry.
In that notch angle get 90 degree. That mean what?
Negative. Okay. It must have actually this complex conjugate pair. Otherwise, you don't get the. It's imaginary plane. Yes. It's imaginary. So these are zero pole plot. So zero pole plots for a system which has a real number coefficients has always complex conjugate pairs for zeros and poles. Notch at 90. No, my notch is here. Okay. let's move on, and I'll show you exactly what I'm talking about here when we go to the exercise. Okay. Okay, but those classical filters and the same filters you have played with on your analog electronics, they are these digital corresponding filters, which are transferred to the digital domain using the this bilinear transformation, and then how to get rid of that nasty nonlinear phase response is to make the zero phase filter, meaning any filter, whatever the this phase response is, this trick makes the output signal to have zero phase shift, meaning the group delay is zero, constant zero. Okay, just a curiosity, median filter. Median filter is used to take out erroneous data points. For example, dead pixels in image. Or if you have a snap, a single once in a while you get bad values on your data, single bad values, then you might actually consider using median filter, meaning that you're replacing the value. See here, does n equals minus n block mean symmetrical window? No, this actually means that you are time reversing the data. So here you have x of n at that point. Okay, now I can annotate again. Text with red. At this point, you have actually the system, for example, system is S, X, Y, Z. Now Z, A. Output A. If this is output is A, then basically after this one, it's A of minus N. So that is the time reversed signal. And here we have B, output B, and at that point we have the B minus N. Okay. I should add those also on the final picture. Okay. But anyways, median filter, that takes out single data, but if you have rapidly changing data, or if you have, it also filters the data non-linearly. So it's quite dangerous operation, and there's no reverse operation since it's a non-linear, meaning that there's no inverse operation for median filter. So basically what it is, you calculate the median of subsequent samples and replace the value. Output value is the median value. Okay, so for example, if you have a 5 points, it's center value of ordered table. So if you have data x as 1, 5, 2, 4, 9, then the middle value actually is, when you order this, the middle value is 4. Okay, median. So actually it's a nonlinear, but it reduces singular peaks from signal. Example on the median filter, ring of the dead pixels, single bad values. If there is a bright spot or black spot, when you run or here we have a red pixel, we basically calculate the 3x3 median and replace that value with the that median Whoops, there it goes. It's as gray as the others. And it works. Okay, match filter, just a curiosity, radar technology. Fundamentally, you use the the same signal as you send it as output, you time reverse it and use that one as the on detector, the you received reflected signal, you pass through that one. So basically the noise will be optimally eliminated there, and this one passes the signal, reflected signal as it is through the system. Okay, this is done. That's the trick how you can get, say, attenuation levels of 200 to 300 decibels in radar, where the signal is very, very, very small when it comes back. You still can actually get it from that tiny, tiny signal from a lot of noise. Okay, and you can actually then have these radars, the weather radars, which are actually measuring the refraction index changes in radio frequency on the atmosphere, and that signal is not much what comes back. Okay, but anyways, match filter used in radar technology, just as a curiosity, and then some. Okay, good. So, wow, that was a long session, but now you have the a brief introduction to the topic. Next, we will have a break.